So in the last video, we looked at the difference between generators and motors. Specifically, we looked at generators and talking about how the motion of a coil in a background magnetic field produces an EMF in the coil. Now, what we didn't really specify there, because we're going to talk about it here, is that EMF that's induced produces a current, which produces a magnetic field which interacts with the background magnetic field to oppose the motion. Right? This is pretty standard at this point. I'm hoping we're seeing our way through it. Nature hates change, right? So any EMF induced in the coil is going to be such that the change in flux it tries to counteract the change in flux, I should say. The upshot of that is mechanically is that it controls the motion. It's a magnetic braking effect. It doesn't necessarily stop it, but it provides some sort of physical, mechanical resistance to the motion. So I have here a really, really simple circuit diagram. Let's imagine that this is representative of some circuit. So I have some source voltage here. This would be my battery or the wall that I plug my circuit into. Whatever is providing the voltage that's being delivered to my load. Load is just a word for whatever stuff you hook up your circuit to. If this is an electric, if it's an oven, the oven would be your load voltage, or your load. The oven would be your load, and it would have some sort of load resistance R. So there's nothing new here. I'm just using this term load to cover up a multitude of stuff. There could be 7 different electronic devices in here. I'm just putting them all together. What is the total resistance that I see here, and just putting this here. So this could be as simple as a light bulb, as complicated as an electric train. So just go with it. There's some sort of load here, and there's some sort of source voltage there. Now, furthermore, let's assume that this load has some sort of electric motor. That's not hard to imagine, because a lot of things that we normally hook up to source voltages do, like hair dryers or blenders or air conditioning units or actual electric motors. Something in this load here is a motor. It's a coil of wire rotating in a magnetic field. All right, well, what is going to happen there? I'm going to induce an EMF in the coil. I'm going to induce an EMF that opposes the motion. So here's my source voltage, but I'm now faced with the dilemma of, as soon as I flip the switch and put this source voltage in line, and this thing starts to spin, whatever is in here that's spinning, I immediately, in this circuit, appears an opposing EMF. I'm going to draw that in like this. Notice I'm drawing it backwards because it's opposing. So here is what I call my back EMF. I'm going to use the script E for that, and I'll even subscript this with a back. So before this thing starts spinning, before I flip the switch, I have nothing. I just have the source voltage. I flip the switch, this thing starts spinning, and then immediately I get this back EMF. Now, we saw in the last video that the voltage induced in a coil, such as that in an electric motor, such as that in an electric generator, is proportional to the rotational velocity. Now, let's think about this physically. When you first flip on anything that rotates, is it immediately rotating at its maximum speed? And the answer is no. Think of the tires on your car, right? Every physical process takes time. And so when I close the circuit and this source voltage is presented to the load, and the load starts to rotate, then I get a really, really small induced EMF. Small because the angular velocity of this thing is small. But as this thing ramps up to speed, this opposing voltage that's induced in the coil gets bigger and bigger until I'm at some maximum speed, my final omega, and then I've got the full back EMF. So the source voltage here is a constant, assuming that I have good wiring in my house or good batteries. This is a constant. But the back EMF varies between 0, right? Right when I flip the switch and this thing is just starting to turn, I have no back EMF. But as it starts to turn, I start to pick up one. So this varies between 0 and some maximum value. We'll call it E max, which is given in the previous video, right? NAB omega sine omega t, or that over 2 if you're looking for the average. Right, so this thing varies. So as soon as I turn this on, I get a little bitty back EMF, but as this thing ramps up and ramps up, I get more and more until it reaches some maximum value. What does that mean? Well, because I've hooked these batteries up backwards, the total voltage to the circuit is actually now decreasing as this moves up and up. How do batteries hooked up like this work? If they're hooked up backwards like this, or in reverse polarity, if you will, negative to negative, then the total voltage is going to be V source minus E back. If I were to hook two batteries up, such as the negative terminal, this one was connected to the positive terminal of the other one, then I would be adding it. That's what batteries add together. If I have a 3-volt battery and a 3-volt battery, they would add together to give me 6 volts. But as it is, because this is opposing, it's as if I put in a battery that's hooked up backwards. And so I have to subtract that off from the total voltage. This is interesting though, because that means when I turn on the switch, I've got a 0 here, and I've got a source voltage, which is potentially really, really high. So my total voltage presented to the load is probably really high. But as this thing ramps up and this climbs higher and higher and higher, my total voltage decreases. That turns out to be really important because most electronic devices with motors, like hair dryers and washing machines, are rated to run at a certain voltage. That voltage is probably much, much less than the source voltage, because the engineers that design these things take this effect into account. So when you first turn it on, it's actually operating, it's drawing a lot of current. What I'm trying to say is it's operating over specs. It's drawing more current than it's rated for, probably. But very quickly, this back EMF gets up and up and up, and you get into your spec range. That's good, because if you draw a lot of current, think of what happens to current flowing through a resistor, right? What happens to the resistor? It heats up. There's power dissipated by this resistor. So if I'm drawing a lot of current, if this back EMF didn't exist and my source voltage is very high, I'm going to burn up my electronics really, really quickly. And in point of fact, that can happen. If you're ever dealing with something that's rotating in an electronic system that gets stuck, what you should do immediately is turn it off. Because if it gets stuck, this goes to 0, and the total voltage presented to the load is very high. It starts to draw a lot of current, and chances are it's going to heat up and melt down, or some sort of catastrophic failure, because it's not rated to run at this high voltage. It's rated to run at the total voltage, which is going to be less than the source voltage. All right, so let's see how this works. Typical way these problems are asked is they tell you, either they tell you the resistance or they tell you the initial current that flows the nanosecond that you close the circuit before the back EMF has had time to ramp up. We'll do the first way. We'll say that we know the current that flows right after I close the circuit. That is before this thing has had a time to rotate. And let's ask ourselves, what is the resistance then that is in this circuit? How to handle that is just by Ohm's law. Let me remind you what Ohm's law is. V is equal to IR. In this case, though, this is not just a simple voltage, because I have this rotating thing. This voltage will be the total voltage presented to the circuit. So let me rewrite this in terms of what I have here. Source voltage minus the back EMF is equal to IR. Okay. Fair enough, I can solve this equation for either I or R. I can solve it for any of this if I wanted to. But usually a problem will say given an initial amount of current right when you flip the switch, what is the resistance of the load or the resistance of the circuit? So let's think about it. Right when I flip the switch, before this thing has had time to start rotating, what is my back EMF? Back EMF is going to be 0. So right when I flip the switch, this is 0. And then I can easily solve either for the current or the resistance. Let's say that I'm asked to solve for the resistance. I'm given the initial current and asked to solve for the resistance. What I do at that point is say, okay, well then Vs over I naught, because that would be my initial current, is equal to R. Just as simple as that. The physics comes in from knowing that the back EMF is 0 right when you turn on the circuit. Okay, well, what do we do with this? Well, now we know the resistance, and notice the resistance is not a variable. The total EMF is a variable because this component is variable, but the resistance is not. And so then they might say, all right, well, how much current is the thing drawing after it comes up to speed? So I know the resistance now. Let me get a different sheet and solve the next part. So I've still got Ohm's law, but I'm going to write it in this form. And I have determined that R is equal to source voltage over I naught. Now, after this comes up to speed, this is no longer 0. So if I know what this is, solving for the current when it's up to speed is really easy. All right, so I just get the current at speed, I'm going to write it like this, after this thing comes up to speed, is equal to Vs minus E back over R. But I've already determined what R is, it's this. So it looks like if I put that in, I get Vs minus E back over Vs over I naught. I'm happy if you leave it like this. You can also, of course, write it like this. I naught Vs minus E back over Vs. Either one of those works for me. So that's one way a problem could proceed. It might ask you at first to determine, given the initial current, determine what the resistance of the circuit is, which you can do by knowing that E back is 0. Then once you find that, it might ask you to determine the current at speed if they give you what the back EMF is. Another way they could go is to give you the current at speed and ask you to solve for the back voltage. So you still know the resistance. So let me write that equation again. Vs minus E back is equal to IR. So this time they're going to give you I at speed and ask you for the E back. You see what's going to go on here. It's not a big deal. It looks like Vs minus I speed times R, which is this, Vs over I naught, is equal to E back. Just that simple, right? This is actually, Ohm's law is a simple equation. The only thing we've done to it is we've added this other term to determine the total voltage. But after that, it's still just as simple as it was when we were using it to solve circuit problems. It's just in this case, we have this other component, and you just have to know that the maximum back voltage occurs when this thing is at speed. Before it starts spinning, the back voltage is 0, and it varies in between there.